transport of momentum, energy, or mass, okay, which is very frequent, which is what we actually very frequently encounter in engineering related problems, right? This is the general equation, and the meanings of R and D will depend, the physical meanings of R and D will depend on what quantity psi we are choosing. So for example, if I choose psi to be mass, then generation of mass, so this would be interpreted as reaction due to reaction. And this would be basically mass diffusivity. Okay. Similarly, if you choose psi to be, let's say, momentum, then generation term would be like external force, okay, which could arise due to pressure imbalance or gravity, etc. And this would be the stresses that are present in the system, which is diffusive. Stresses are essentially resulting from diffusion of momentum in the medium. Okay? So, okay. And D will be actually having, D will be equivalent to, D will be actually interpreted, D will take the form of kinematic viscosity if I choose psi to be momentum. And if psi, you choose psi to be energy, D will be thermal diffusivity, and generation term can be associated with energy, any kind of energy source you may have in the system, which can actually release energy. For example, you can have nuclear reaction going on, okay, which can release energy. So that would lead, that would give rise to such kind of terms in your equation. Okay. So okay. So and in general, you can have all the three phenomena: momentum, heat, and mass transfer simultaneously proceeding. Okay. And then things you have to basically look for. You have to write equations for each of those separately. They will be coupled. Okay. There will be coupling between those. The coupling will be through this V, because V will appear in all the cases, right? So there will be coupling through this V field, and then there will be overall momentum conservation, which will give me fluid dynamics equation, etc. So that will be lead to the most complex scenario you can imagine in a transport process. Okay, but we will. So, but in order to understand it, we have to go in steps. We have to understand things. You have to understand situations which is much more simpler than the complex ones. Okay, so we'll talk about those as we proceed, and and mostly we will, so the problems that we encounter generally will not be solvable using mathematical analytical techniques, and we have to resort to computing to perform those final, to get your answers, what you predict based on your model. We need to resort to computing techniques, right? So that's what we will discuss en route as we proceed in the course. Okay. All right. So let's first. I'm going to now let me just talk about some simpler scenarios which may result from this general equation. Okay. So one case what I just talked about was we talking about steady state situations, and in that steady state case, del psi by del t will be zero. Okay. And that will invariably lead to ODEs, because in that case I will, and of course, if I have only one independent variable, that means one dimensional steady state case will lead to only one independent variable, therefore it will be an ODE. Okay. Uh, for example, reactions diffusion system that we talked in the last class had this equation, which is an ODE, of course, and it will be having a, of course, there will be boundary conditions to satisfy. All right, so depending on the boundary conditions, this solution will look different depending on what boundary conditions you choose. How to choose the boundary conditions here, we'll talk about that a little later. Okay. First, let me talk about different kinds of modeling equations that we may encounter. Okay. So I think that this example is even little more complicated. Let me actually look at the simplest situation. So simplest situation would be when everything is zero, right? So so you see that what causes what are the important things here? What are the important phenomena? Well, let me just rewrite this. Del psi del t plus del dot j would be consisting of psi times v plus, sorry, the minus sign, I guess, minus d del, generally three-dimensional case, I will be having this situation equal to generation term. Okay. Yeah. fine. Okay. Now, what are the things here? One thing I just want to emphasize here. This thing del psi by del t. Remember, it's a rate of accumulation. This is what we observe. What we observe. Okay. So this is what we measure. So rate of change of any quantity in a given constrained volume. Let's say I can measure total content of that quantity psi in the, and then I can find out its del psi. The concentration of that quantity I can find how it can change with time, right? This is what we observe, and this is basically what is responsible for what we observe. Okay, so this response, what is causing the change in psi is due to flow, inhomogeneity, and generation. These are the three things which would cause a change in psi with time. Okay, so what is responsible for what we observe? Okay, and these are the basically flow, which is the convection part, inhomogeneity, meaning gradient in the psi, okay, del psi by del x, because if del psi by del x is zero, your this term will disappear, okay? So this would only matter when there is inhomogeneity in the system, or generation. Okay, so these are the things which are responsible for what we observe. That is, accumulation or depletion will occur because of basically interplay of these three phenomena. Right? Now, now what we are going to look at is, let's consider simplest situation when no flow, no inhomogeneity, no generation. There's nothing present. There's no everything homogeneous. Nothing is flowing, and there is no generation. Nothing is happening. There is no source of any quantity present there. For our sake, let's assume psi. For now, let's assume psi to be mass or mole number of moles, okay, number of molecules. So let's assume that. So in that case, basically psi would be Ca. Ca. So concentration of any species will be the small psi. Okay, this is big psi. Okay, so let's think in terms of Ca. If psi is taken to be Ca, then del Ca by del T will be zero. There's nothing, no change, nothing is happening. That's a trivial case. Okay, there's nothing happening actually. Just things are static, uninteresting, boring case. Let's make it a little interesting by saying that, okay, let's say there is no flow, okay, no inhomogeneity, but reaction going. Okay, so I have this term present. Okay, remember generation term. If I choose psi to be Ca, generation is basically associated due to reaction. Okay? Masses can be changed because of chemical reactions. Okay, or number of molecules can change due to chemical reactions because of chemical transformations. Their chemical identities will change. Okay, so reaction is happening. Now we can consider the situation del psi by del t. If there is no flow, that means velocity is zero. No inhomogeneity, meaning psi or Ca is del Ca by del x is zero. Let's think. So inhomogeneity meaning del Ca del x zero. So let's say del Ca is equal to zero. What does that mean? That means Ca is constant in space, right? Everywhere the concentration is same. Okay, how would you achieve that? Is it something that you can easily achieve? Well, it can be achieved. It can be, this condition can be met. Okay, this condition can be met by, yes, mixing. Exactly, absolutely. So absolutely right. So this can be obtained in mixing, or if there is another situation where diffusivity is very large. Okay, so remember diffusivity is a property of the medium. Okay, so diffusivity is basically is a tendency to homogenize any concentration gradient. So if the diffusivity is large in a medium, then medium cannot sustain concentration gradient. It will quickly. So imagine like you putting a small peck of ink on a blotting paper. Okay, it quickly spreads out. Okay, and becomes homogeneous in the region where it's spread out. Okay, so we can imagine, we can assume that the time it takes to spread out is so small because of very high diffusivity that we can ignore. And for most part of the time of interest, it is nearly homogeneous. So when D is large, we can assume Ca to be uniform. If I know that, if I'm for sure that D is large, then I can assume that. Or there is a vigorous mixing so that any inhomogeneity caused due to low diffusivity is basically, you basically, when you mix it, you try to homogenize it, which would have been absent if you had not mixing, and there would have been a diffusivity would leading, I mean, low diffusivity would lead to a concentration gradient, but it would be basically balanced out by mixing. Okay, so let's say I have a mixed, I have either mixing, or let's say D is very large, but D will not play a great role because we're assuming anyway that del psi is zero. So let's say by some means I'm going to assume that Ca is del C is zero. Okay, so this term is zero. Okay, this is zero. I'm going to have del Ca by del T is equal to R. Okay? So I'll be getting, sorry about that, del Ca by del T equals to rate of generation of R. Okay, this is a very simple relation we all know about, right? Okay. Uh, now, um, so this, now RA I can get from what? Now, well, um, this is what? What is this kind? This is basically what? This is an ODE and special kind of ODE, which is initial value problem. Okay, so so basically what's going to happen is there will, the kind of problems we'll discuss will fall into different classes for which solution procedures would be similar. Okay, so that's why we are going to, like, initial value problems will have one kind of solution procedure, boundary value problems will have one kind of solution procedure, etc. Okay, so that's why we just want to make sure that you identify the problem by looking at the model equation. Okay? All right, so this is basically initial value problem. What does initial value problem tell me? It tells me that, so now remember, this I can find out, the right hand side I can find by doing independent kinetic studies, and let's say R equal to minus K Ca, okay, or K C raised to n, let's say, to keep it general, okay, or it can have more complicated form. Okay? It need not be a elementary reaction, and it can be bunch of reactions together, which will give you the order appearing as some complicated expression on the right hand side. So that can be obtained from kinetic studies. So anyway, so this would be this would be essentially a batch reaction, batch reactor, where you have everything inside. It's like cooking something. So you have everything here. You have completely stirred. Okay, products are stirred, and you're having reaction going on. No flow, because it's a batch would mean that no flow. Okay, everything is contained inside this, and since you're stirring it, so there would be no homogeneity. Okay, only reaction will be present, and that would be given by this equation. So this will give me a transient behavior of Ca with time. Okay, so how Ca changes with time? C as a function of time will be obtained if you can solve this. Okay, and that is something that you can check. Okay, so anyway, so this is actually used for studying kinetics in labs, right? Okay, now um, now um, when the reaction completes, let's say, del Ca by del T will be zero. Okay, when all the A is consumed, del Ca del T will be zero. Okay, and you will have steady state, so-called steady state in this case also, when the reaction is nearly complete. And so when reaction is complete, okay, then there will be steady state. Okay, now let's make the problem a little more interesting by Consider this problem. Now I have, let's say, more than one reactions going on. Okay. And let's say A transforms to B with some rate constant. Let's assume they are all first order. B transforms to A with some rate constant K2. B transforms to C with some rate constant K3. C transforms back to B with some rate constant K4. A transforms to C and C transforms to A. Okay. This is my this is something known as chemical reaction networks. Okay, so reaction networks, and they are very important important uh, processes, or you can say important things to tackle when we talk about biochemical systems, right? So in your cell, for example, there are myriads of reactions going on, and they're all like they form like network of reactions. So there will be side reactions, and then that giving you some more product. That product will be reacting with something else, giving you some other product, and eventually returning back to your original reactant that you started with. Okay, so there can be very complicated looking networks possible. Okay, but I'm looking at a very simple looking network that's over here. Okay, even much simpler network, the simplest network I can think of is this one, where A and B, A gives you B, B gives you A. Okay? That's simplest network we can imagine. Anyway, but this is a little more complicated than the first one is little more complicated than the second. Let's say now if you write this, what is going to happen? Del CA by del T is going to be equal to K1 CA, okay, minus plus K2 CB del CB by del T. I hope you all are familiar with this, how to write this, right? Minus K3, C must have studied it in JEE, right? Plus K4, CC. Please correct me if I'm making a mistake, but I not to. Del CC by del T would be equal to minus K6 CC plus K5 CA. Okay. Now, okay. So this would be again an initial value problem. This is kind of generalization of simple reaction, let's say this, where this was given by del CA equal to minus K1 CA, let's say, okay? If I had just simple reaction A giving you B with some known rate constant, then del CA by del T is minus K1 CA, okay? And this is initial, why, so yeah, I was talking about why is it called initial value problem? Well, because I know CA equal to CA0 at T equal to T0. I need to know initial concentration. So knowing the initial value, what you do is you march in time. So then you find T0 plus delta T, what would be CA? Then T0 plus 2 delta T, what would be your CA? Okay. This problem is exactly what AC is also contributing. Yeah, yeah. Oh, right. I did not write other terms. There should be 4 terms. You're right. Absolutely right. Sorry about that. Absolutely right. Yeah. So for B, I should be having 4 terms, not just 2 terms. For each of those, I should be having 4 terms. Yeah. Just a second. I'll just correct this. So BC minus K1 CA plus K2 CB minus K5 CA, okay, plus K6 CC, okay. DCB dt would be equal to that K3 CB, K4 CC minus K2 CB plus K1 CA, and dCC dt would be equal to minus K4 CC plus K3 CB. Okay. Anyways, well, you all know how to write this. Please, I'm not worried about if I made some mistake there. Please correct it. That is not the point. That is beside the point. Okay. Just look at the details. I'm not interested. I will at the moment. I will not be interested in details. Of course, when you solve the problem, you have to be careful. But if I made a mistake, please point it out. I'll correct it. But yeah, I think I wrote it wrong the first time. Thank you for correcting me. All right. Anything else? CB K1 C minus K2 CB. CB is, yeah, I added that. So yeah, there was additional term. In all the three terms, there will be two more terms, all the three cases, all the three cases. All right, well, this equation that I just wrote, if you have first order, yeah, first order, we all know the answer to this. So CA will be equal to CA0 exponential minus K1T. We all know that. This is from mathematical analytics and just integrate it simply. But there may be situations where you may not be able to integrate if right hand side has some complicated form. Okay, it's not just CA but CA over, let's say, 1 plus CA, something like that. So then it's possible to have right hand side, so that difficult to be integrated analytically, and then you have to resort to computing techniques. And when you implement computing techniques, what you do is you start with initial known value at t equal to t0, and then find out CA at delta t little later, and use this information and previous information to find CA at 2 delta t. You can find, so basically, if you know t equal to 0, if you know CA value over here, let's say CA is over here, and del CA del t at this point is known, you use this equation to calculate your CA at next step values. Okay, you can get your CA dependence on time. Okay, so you proceed by little bit in delta t, and keep on finding out CA, etc. at each next point, okay, in time. So that way you solve or you numerically integrate the equation. Okay, this axis is CA versus T. All right, so this is what you are essentially doing, is you are marching in time. These problems essentially, uh, you do marching in time when you try to solve it. Okay, start here and then keep on moving on time axis step by step, and at each step you keep finding your new CA values, concentration values. Okay, so that's why it's called initial value problem. You start with initial value and then march in time. Okay, anyway, so this would be your initial value problem if I had only one dependent variable, that is CA. Now, if you look at this problem, I have more than one dependent variables. Only one independent variable, which is t, but more than one dependent variable that looks like this. Okay, how to solve this? Okay, well, this is basically a system of IVP. Basically, so basically it's again same thing. It's an IVP. It's an initial value problem with many dependent variables. Okay, and the way to write this would be you define a vector of concentration. You can call it C as CA, CB, and CC. Okay, and you can write down dc dt. All the three equations can be together represented as this form, which is, so now if I just look at this right hand side can be represented in a matrix format, where I can write down CA, CD, CC like this, and there will be some matrix elements over here. All you need to do is just separate out CA. So for example, this element will be equal to minus K1 minus K5. The first element will be, is multiplied with CA. Okay, so minus K1 minus 5, K5. This element will be K2. This element will be K6. That will give me dCA dt. Similarly, this element will be equal to K1. Okay, so maybe I can write, so let me just point it out over here. Okay, and A I can write down as minus K1 minus K5. Right, K2 and K6. K1 minus K2 plus K3 and K4, and CC will be having K5 here, CB K3 and K4 plus K6. Okay, and C is, of course, this C is essentially a column vector. of Ca, Cb, Cc. So you can think of tracking all the three components together. Okay, so this differential equation is basically again an ODE but in multiple variables, and that's a way to write this. And how to solve this equation? Well, we'll talk about that. Okay, so it has a similar procedure as this form. Okay, all right. Now let's look at an even simpler problem, simpler situation of this. I'm just going today and the next few classes maybe. I'll just give you a flavor of problems that we are going to meet, and then we'll start talking about the solution techniques. All right. All right. So this is we can further simplify. We can talk about equilibrium situation. Okay. We can ask what happens in equilibrium in this network. If it achieves an equilibrium, what's going to happen? Well, the steady state will be achieved, and left hand side will be zero at equilibrium. Okay, what are we going to get in that case is the following form, which is generally a equilibrium condition will give me AC equal to zero. Okay, which is sorry, AC equal to zero, right? So this would be so this would be a problem uh, that would be actually associated with. So this is kind of something known as linear systems. These kind of problems you basically try to solve by. So you all are. So I'm not going to spend too much time on linear system because mostly we'll probably be talking about differential equations. But in this problem, what are we going to get is actually an algebraic equation. Algebraic equation in C. Okay, or CACBCC. What is so this would be like A11C1 plus A12C2 plus A13C3 equal to 0, B11C1 plus B12C2 plus B13C3 equal to 0, and so on. Okay, so this is basically this is not differential algebra because you don't have derivative terms appearing here. Okay, all right. Now how to solve algebraic equations? Well, uh, let me make the steady state equilibrium condition. You can hold on to the equilibrium condition, but let's make the equations a little more complicated. Let me say my equation network looks like, for example, one problem that I have here is, let's say, 2a plus b giving you c, okay, and a plus d giving you c, okay, and let's say I have CA0, CB0, etc. given. Okay, so CA0, let me see. I have the problem stated over here 40 units, whatever units is relevant there. I will not write the units at the moment. CV0 is 15, CC0 is 0, CD0 is 10. Okay, and we are also given the equilibrium constant. So you all probably are familiar with equilibrium constants. So the first reaction equilibrium constant is given basically Cc over Ca squared Cb. Okay, and that is value is given to be some number, and A2 is given to be Cc by Ca Cd. That is 4 into right, 4 into 10 raised to minus 2. Anyway, those are just numbers that we can change later, but so if you look at these kind of equations now, what is different in this as compared to the previous case? Okay, the difference is suppose I'm going to write down dCA dt, or let's say I'm going to write down well, you can write down. I hope you are all familiar with it. dCA dt would be equal to actually, maybe I can just think of steady state case. So in equilibrium, okay, what's going to happen is you have K1 Ca square Cb minus Cc equal to 0. Okay, and then additionally CaCd K2 CaCd minus Cc equal to 0. Is that all right? So this, if you just use these numbers, I'm going to get these equations in Ca, Cb, Cc, and Cd, of course. Okay. All right. So these are the kind of equations I'm going to get in terms of my unknowns Ca, Cb, and Cc, which would correspond to equilibrium. So remember this relationship. These are my equilibrium compositions, concentrations, right? So okay. So this is what I'm going to get for equilibrium conditions, right? Now, if you compare with this and this, what's the difference between these two? The difference is that I have non-linear terms appearing. This kind of equation which we saw in the previous case here, okay, this kind of problem did not give us any nonlinear term. And why was that? Because it was a first order, okay. But if you have higher order reactions involved, okay, that is K1 Ca raised to n, where n is not equal to 1, then I'll get nonlinear terms over here. Okay, that is what is being reflected over in this case. I have 2A appearing, that's why I have Ca squared. I have two molecules, actually three molecules reacting to give me one molecule. This is not a single, so order is not one. Okay, so therefore I have net order being equal to 3, therefore it's a nonlinear term that is appearing because of that reason. Okay, so this is an example of something known as non-linear algebraic equation. Okay, all right, so that would form one, that would be actually useful. So that would be good to know. It's actually good. We'll be talking about nonlinear algebraic equations. But so let me just spend a little bit more time on this, because this will be very useful when we solve even differential equations. When you try to solve, this tool of finding, or this knowledge of solving the nonlinear algebraic equation will be very useful. All right. So let's see. In general, suppose I have only one variable. Okay, and this is something that you must have studied earlier. I'll probably repeat it. So you have some function of x. Let's call this x. So some function of x is equal to 0. Okay, and this function is a nonlinear function of x. Okay, the simplest case that you are probably familiar with is x squared plus bx plus c equal to 0. Okay, that can be solved analytically, but that's the only nonlinear equation that can be solved analytically. Others, you can general have no form, closed form. Okay, so other equations, if you have general other form involving e raised to x, sinusoidal functions, exponential functions, transcendental functions, logs, etc., then you will be, it's not just easy to find. So basically this is essentially a root finding problem. Okay, root finding problem. You have to find what is the root of this equation, that's all. For what value of x, the left hand side, the expression is equal to 0, right? So okay, and how to do that? So if you have nonlinear algebraic equation in one variable, do you all remember any technique that tries to solve that? Anyone who knows? Yes, Newton-Raphson, right? So absolutely, Newton-Raphson is a method. Yes, Newton-Raphson. So I recommend that you review this, but I'll just quickly do that. It's a very simple technique, but remember, I just want you to be aware of the catch, what are the possible catch points in applying this technique. It's not a universally applicable. It's not a universally applicable. Okay, practically, it does not work everywhere. Okay, so you have to be aware of where, what are the situations where it may not work. Okay, not a universally applicable technique. But generally speaking, if you are smart enough, if you are clever enough to guess a value which is close to the root, okay, you always start with a guessed value, and then this technique actually it's an iterative technique, meaning you start with a guessed value, and then it basically the technique leads you from the guessed value to the correct root, okay, in a very efficient manner, okay. So the thing is that if you are clever enough, you are smart enough to guess a good value, which is not very far off from the actual value of the root, then you will get the correct value in very few number of steps. Okay, so that is the thing. But if you are very far away and the function itself has certain properties, then you may get into trouble. You may never get the correct value. Anyways, so let's assume that our function is such that, or our choice of guess value is such that it's applicable. Okay, so let's say uh, graphically, I'll just explain this. Well, you all know that. So suppose this is my function f of x, and this is my x. Okay, and this is the point where I want to find which I want to find out. Okay, so Newton suggested that okay, you start with some guessed value. Let's call that x0. Okay, and then approximate the function at this point as a straight line. That's all. That's a basic idea. Okay, so approximate the function at this point. How do you approximate that function at a straight line? Well, you imagine you know the function, so you know the derivatives. Okay, so you can find that f prime at x. Let's say yeah, tangent, of course. So tangent, you draw the tangent line, and then you find where the tangent cuts this x-axis. That will be your next value. Okay, and then again do the same thing. At that point, you get the tangent again. You get the next point x2, and you keep on doing it until you meet certain tolerance limit, until you are happy enough, okay, until you are satisfied with your answer, that okay, I'm close enough to my answer, so that it's not improving at all. So just keep on calculating fx. When it's very close to zero, you stop. Okay. So this procedure, you can check back. I will not write simple. I'm not going to show that. You can show that yourself. At any step xi plus 1, you basically you improve. So this will be delta x, right? So delta x 0. So at each step, there will be a change in x. Okay. So the step size in x is given by xi plus 1 minus xi, that is delta xi. That is given by fxi divided by f prime of xi. That's correct. Right? Yeah, that is right. Okay. So xi plus 1 is given by with a minus sign. Xi minus f of xi divided by f prime of xi. That is the technique. And anyone who is not familiar with it, please let me know right now. Who is not familiar with this technique? Class, anyone who is not familiar with this technique, you have to let me know right now. Okay, so I'm assuming that, since I'm not getting any answer, so I'm assuming that, yeah, everyone is familiar with this. And you also know how to implement it on computers. Okay? So that is another thing I would be requiring you to know. Okay. All right. So starting with some guessed value x0, okay, you should be able to find the x which satisfies this condition. All right. Now this is so far so good, but now question is, how do you do? What do you do if I have more than one variables? Okay. So now I have, let's say, more than one variables. Okay. Meaning I have variables, like for example, what I saw in the situation of when we were required to solve concentrations in a complex network reaction, when we had to find when the reactions were not first order, okay, that gave to nonlinear algebraic equation in several variables. Okay. So I have, let's say, variables. I'm going to write it as a vector component. Okay, so let's say my variables are x's. Okay, so I have x1, x2, let's say n variables. Okay, these are my variables. Okay, these are my variables whose value I want to find out. And these n variables satisfy n equations, which are nonlinear equations. So I'll have f1 of x1, x2 up to xn, that will be 0. f2 of x1, x2 up to xn, that would be 0, and so on. I have n equations which are independent equation. I'm not going to bother about how to check whether they are independent. We'll assume that they are all independent equations, and these are one or more of these can be nonlinear functions. One or more of these functions may involve nonlinear terms in terms of its arguments. Okay, there may be product terms or squared terms or cubic terms. We can have x1, x2, or x1 square, or x2, x3, etc., or 1 over x, x5, etc., log of x5, sine of xn, is like that. Okay, you can have nonlinear terms present in your expression on left hand side. These all together, actually, I'm going to write in a shorthand, will be f of x. Vector will be 0. Everything is written in a single notation. F would mean I am talking of many functions. Okay, I have f1, f2, f3, and arguments are also vectors x1, x2, x3. Okay, okay. Now you tell me how to solve this. Can anyone tell me? Does anyone know? Doing the same matrix. Yeah. What is the matrix formation with NR method? So my question is, okay. First, let me ask you this. If I have, what is the mathematical condition that must be fulfilled? Forget the matrix. Just tell me if I have multiple functions, I want to find out for what values of x's will this function be minimum. Okay, or oh, well, this function will be 0. What is the condition for that? All right. Well, okay, maybe I can, well, maybe I can just directly give you the result. So it is basically uh, given by, so let's say at any, what you're going to do is you will have an initial guess of each variables at, let's say, 0th step. That's initial guess. Okay. That is something that you have already done. You have made a guess values of all these values. For example, in equilibrium calculation, you made a guessed concentration. You made initial your own guess of concentration at which you expect them to be at equilibrium, and then you actually update those values by certain scheme, which is Newton-Raphson scheme. So what is that scheme? By what rule do you update? Well, it's basically based on simple. Well, if I just write this down, if I just write this as delta x, if I just write the equation for one variable, what did that say? It said that delta x should be equal to minus f of x divided by f prime of x at any step I. Okay, at any iterative step I, at any iteration I. Okay, this is, you find delta x. Okay, you know xi, you find delta x. Okay, and then update xi plus 1 by xi plus delta x. Delta x, I can just write it. Xi is, say this is I. Okay, so that was a scheme. In order to apply to this situation when we have multiple variables, what we do is actually write this in this form. Minus, well, f prime x delta x at step I would be equal to minus f of xi. Okay, I just write it in this form. Okay, and then apply this to this situation of multivariable case, multivariable multifunctions. Okay, how do you apply that? Well, you say first of all, right hand side will be a vector, delta x will be a vector because x's are vectors. So delta x will be replaced with the delta x, sorry, delta x vector. Okay, equals to minus f, okay, x step, and f prime x is basically a matrix. What is that matrix? How do you calculate f prime if I have not a single f but many f's and many x's? Okay, well, this is a vector. This is defined by aij equals to del fi by del fg. That's as simple as that. To construct this matrix, meaning f11 will be taking first function, taking its derivative with respect to first variable. fa12 would be equal to taking first function, taking its derivative with respect to second variable. And a13 will be del f1 by del x3, a14 will be del f1 by del x4, and so on. And an1 will be nth function with respect to first variable, second, and third, and so on. So that way you construct the A matrix, okay? And at ith step, yeah, I already know xi. Okay, ith step because it's an iterative scheme. So knowing current value, I'm going to get the next better value. Okay, if I know current guessed value, which is xi, I can find out the right hand side. Okay, which will give me a, let's say if I have n variables, then this will give me a set of n numbers. That will be like a column vector. Right hand side will be a column vector f1, f1, f2, f3, etc. at a given xi's, okay, that would be equal to, this would be delta x1, delta x2 up to delta xn, and you will have a11. Well, I can write this as, to make it more explicit, that would be del f1 by del x1, del f1 by del x2, and so on, up to del fn by del x1, del fn by del x2, and this term will be del fn by del xn over here. Okay, so this is at ith step. Okay, this is at ith step, and this is at ith step. This would be f1, f2, f3, etc. with a minus sign, of course, over here. Okay, so this is known to me. So basically, this is known to me. This is known to me at ith step. This is what I want to find out. This is my unknown. So this is nothing but again a linear system. Okay, I have these quantities, values. These are numbers. These numbers are known to me. These numbers are known to me. I can construct this matrix with the given numbers. I can find it out. These numbers are known to me. These numbers are not known to me, but I know that this is essentially a linear system. It's a linear equation in terms of delta x1, delta x2, delta xn. I can solve it by linear solver, and you all are probably familiar with how to solve linear equations, right? Linear systems using Gauss seidel or Gauss elimination, etc. Okay, so I want you to be, please review that. Okay, so if I give, you should be able to solve it. Okay, so that's how you update your delta x's. Okay, and once I updated delta x, then I can get to a better x vector. So here I'm going to get delta x, okay, at ith step will be obtained by this Newton-Raphson in multidimensional case, this one, and then that would be added with xi, that vector that will give me xi plus 1. Okay, all right, that way, that is the way of improving your values, okay, and getting closer to the condition where all these equations are simultaneously zero. Okay, now my question is, when do you stop in this case? How do you stop? Any answer to my question? The question now I have, yes, it's partial derivative, of course. Rohan, I'm answering your question. So these are essentially partial derivatives, of course. Absolutely. Absolutely. Okay. So yeah. So now my question is, when do you stop? How far do you keep on going forever, or at some point? Yeah. Okay. Value of the function. Now, how do you define the value of the function? I have several of them to be. It may turn out that fn is not close, but all the others are very close. What would you do in that case? So my question is, which function you are going to look at? You have a number, and you have to compare to zero for all of them, and it's not necessary that all of them will actually fall simultaneously to close to zero. It may so happen that one of them is quite off, but all the rest are very close to zero. In that case, would you accept that? What linearly independent? No, I mean, my question is, I got some xi plus 1 value at some at iterative step. Suppose some iteration, I get some xi's. I calculate f1s, f2, fn. Okay. My goal is to have all of them equal to zero, but it may so happen that some of them are very close to zero, and one is probably very off. Would you be happy with that? What would be your condition when there will be no significant change in, well, how do you find delta x? Okay, that is one way. Okay, that is one way. Okay, so that is okay, but that actually will not. So when delta x is small, that is possibly a way to, that is possibly a condition to stop. But the question is, will it satisfy what I desire to be satisfied, meaning all the functions? It may so happen that your delta x is not improving, okay, but your function is may not be, is also not zero. For example, I can give you an example. That's a good point that you raised. For example, in one variable case, okay, in one variable case, you may have a function that is not zero at all. Okay, so suppose I have a function f of x which does not have a root. Okay, it may look like this. Let's say, and this is my x equal to zero. It may so happen that you go over here, and then you can choose value which can actually keep on oscillating, and you will probably be you will reach very close to zero. You may be actually even oscillating, but you'll never get fx to be equal to zero. Okay, so having delta x significantly small, that is fine. Okay, but that need not ensure that you have found the root. Okay, it can also say, it can also tell you that you are probably not improving. Okay, you're not changing much. So uh, it may also be a signal to the fact that your technique is not giving you desired result. It's not getting you to. It's not actually giving you better results, or it's not leading to any correction or any betterment in your value. Okay, but the thing is that you may not still be sure that whether it's a function is all the functions are zero or not. Okay, that you have to check anyway. So this can suggest two things. Either you have reached your spot, okay. So either the desired uh, desired condition is met, or the condition is not met, but my technique is not helping me. It's not helping me anymore. That is another reason you should stop, right? If you know that you're not getting anything out of your current techniques, then you have to stop, because it's not going to help you. Why to let it run? Okay. So in any case, to check whether the desired condition is met, I have to find whether the functions are zero, or whether function. So this will also tell me, in order to find whether the condition, whether my functions are zero or not, I have to do that test anyway. So my question goes back to the same. So I go back to the same question: how do you test whether the functions are zero? I mean, the question is, if all functions are nearly zero and one of them is probably a little off, what would you do in that case? What would be the most judicious way of deciding, okay, now I can stop. Well, so basically that brings to the idea of something known as norm. A norm of a vector, and a vector is nearly zero. Remember, a vector has many components. And when do you say vector's length is zero? Well, you when say vector is zero when you say its length is zero, right? Basically, in this case, if you just look at the f1 square plus f2 square plus f3 square, all up to f1 square, square root of that, well, or even this square root. But if the sum of the square is zero, then you can stop. Okay, so there's a condition that involves all the f's. Okay, and you can just think of it like a vector having some kind of length. Okay, and when you that length is zero, you're going to stop. Okay, because you want that would be one of the criterion, but you can devise other criterion as well. This is very frequently used criterion to stop. Okay, so criterion stop. Okay, so I think I have talked sufficient about Newton-Raphson for multivariable problem. I want you to now is the time you should be actually familiar with MATLAB. So next class we'll do probably a couple of problems on MATLAB. Okay, and probably involving this Newton-Raphson multivariable. Okay, and then we'll be moving on. Okay, any questions? Akshat? Uh, f1 fx1 into fx2 is less than zero condition. How will that work, Shalu? Yeah, it's like a mean square error. Akshat Pandey, you are right. Absolutely right. Yes, of course. If one function is, so I'm answering uh, Rohit's answer. If one function is off, then norm will also never be zero. Of course, yes. So you just reject that. Then you keep on working. You don't accept that. That's fine. Exactly. Absolutely right. But at least it gives you, yeah. So it gives you a way of an unambiguous way of deciding when to stop. But what I'm saying is it's not the only way. You can devise your own way. Some people would look like, for example, what is the maximum f? So some of these are different kinds of norms defined for a vector. In mathematical language, it's called norm. So how do you measure the uh, magnitude of a vector? How do you estimate the magnitude of a vector? So one way of saying that is just max of f component. So fi is, if you just look at maximum value of f1, f2, f3, that is equal to 0 or close to tolerance limit, you can stop. That's another way of stopping. So you can say that, okay, I'm going to compare all the f1, f2, f3, f4, whichever is the maximum, I'll compare that to my tolerance limit. If that is achieved, I'll stop. So that's another way. That's another measure of magnitude of a vector. Okay, but it's up to you. Usually, this works. This works better. Okay, and why that works better? And we have to go to theoretical mathematics. We are not going to go into that. But it's very interesting area. We'll not go into that. It's actually based on what Rohit just mentioned. It's based on least square error being minimized. Okay. But we'll not go into that. We'll just accept that this is the technique we are going to follow. All right, so we'll meet next class, next tomorrow. Link. Okay, hold on. Question. Recording is only with pictorial students. Why? Really? I have shared with both the batches. Let me check. Let me check. I'll do it today. Okay. Promise you to do it today. Okay. By this evening. All right. Then. Okay. Then we'll stop here. Any question? Any more questions? Oh, by the way, I have one. I have a question for you guys. How is material science course coming up? And for that matter, any other course. All the so please let me. You have to keep me abreast of other courses also. How are they going? Especially chemical engineering students. Okay, so that we can keep track of things. Okay, you have to let me know if there is any concerns or issues. Okay, please keep that in mind. Or even if you like something, you have to let me know that sir, this course is very good. This course is some discrepancy or something, some deficiency, etc. All right, so please let me know. Even my course also, how's this course going? You please feel free to criticize. There's no, you will not be penalized for that as performance. Okay. All right, so we'll stop here. All right.